In this section, we will be looking at the concept of permutations. A permutation is an ordered arrangement of items. In order to calculate a permutation, you do need to become familiar with a new operation. It's called a factorial, and a factorial has the symbol exclamation point. So when you see an exclamation point in mathematics, it's referring to this new operation. It's defined by n times 1 less than n times 1 less than 1 less than n, and so on. And you just keep subtracting 1 and multiplying until you get down to 1. By definition, you'll want to memorize that 0 factorial is equivalent to 1. Now that may sound confusing, all of it, so let me go through some examples, and I think that after you see some examples, you'll probably see that factorials are not that difficult to comprehend. Keep in mind you can simply type in this 6 and then that exclamation point on your scientific calculator, and it will give you the result. But it's also helpful to understand how to calculate or evaluate a factorial, because sometimes you'll need to simplify some things in addition to being able to use your calculator. So here's what it would look like. 6 factorial, it just means 6 times 5 times 4 times 3 times 2 times 1. Do you see why I'm going to stop at 1? Oh, I forgot the 3. 3, 2, 1. If I kept going and added a 0, it would always just be 0, wouldn't it? So we don't include a 0. We always stop at 1, and that's all there is to it. So if I multiply 6 times 5 times 4 times 3 times 2 times 1, I'd have the final result. I can do some of this arithmetic just mentally, because 6 times 5 is 30, 4 times 3 is 12, times 2 is 24. So if I do 30 times 24, I get the end result 720. But I could also simply put 6 exclamation point on my calculator, and I'm going to get to the 720. Now, if you're using a Texas Instruments 30, you might not see an exclamation point. So what you'll have to do is hit the probability button. It says PRB. And when you hit PRB, you use the arrow to scroll over to the exclamation point and hit enter, and you'll see that you get 600 or 720 rather. So that's how we'd calculate 6 factorial. Let's try number 10. Number 10 here is 8 factorial. You've got it. It's just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You know, I'm going to group this 5 and 2 together to get a 10. 8 times 7 is 56. 6 times 4 is 24 times 3. So if I did 56 times 24 times 3, I'd get 4,032. And then times 10, 40,320. Let's just check that. And you could put in 8 factorial on your calculator, and you'd see that yes, it does in fact come out to 40,320. And then a simple, easy one would be like this number 12. Number 12 is really just testing whether you understand what a factorial means, because it's just 1 times, and then you only go to 1, so it's really just 1. If you need to, I want to encourage you to pause the video and try those calculations. We'll come back to these 13 through 20 later in the video. Let's move on to what a permutation is. And to calculate a permutation, we want to first start with the fundamental counting principle, which we introduced earlier in the chapter, but a reminder that if a first experiment has m distinct outcomes and a second experiment has n distinct outcomes, the two experiments in that order have m times n distinct outcomes. So let's look at how we can use that to calculate the answer to number 1. A license plate number consists of 2 uppercase letters followed by 4 digits. So we have a letter, and then a letter, and then we have 1, 2, 3, 4 digits. So what I'm going to do to solve this is I'm going to start by just drawing an empty line for each of the letters and each of the numbers, or digits rather, and I'm going to write a short description such as letter and digit underneath each one. So when I start with this, now I'm going to go back and fill in how many different ways can I do each piece. So how many different ways can I choose a letter? Well, there's 26 letters in the alphabet. So if repetition is permitted, then after I choose the first letter, when I go to choose a second letter, I can still use all 26. And then when I go to choose a digit, there's 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if I can repeat the digits, if I don't have to eliminate a choice once I've used one, then the answer is 10 digits, 10 digits, 10 digits. By the fundamental counting principle, this means that the total number of options, the total number of different license plates we can make is 26 times 26, which is 676, times 10 to the 4th power. So I'm going to add 1, 2, 3, 4 zeros in there. Can you believe that? There are 6,760,000 different license plates I can use with 7 characters. Let's see how this changes slightly when we look at part B and we say that repetition is not permitted. Well, when I go to choose the first letter, I can still choose 26, but when I go to choose the second letter, and notice I'm going to use the same process, so I have an empty line in which I can fill the number of options, but I have an empty line for each choice. So the first choice I need to make is the first letter and then the second letter, but I can't use the letter I already used. And now I have 10 digits to choose from, but when I go to get the second digit, I can't repeat, so I only have 9 left, 8 left, and 7 left. If you do this multiplication, 26 times 25 times 10 times 9 times 8 times 7, I believe you'll get 3,276,000, but try it on your calculator to make sure that is in fact the result you're getting. Are you ready to try one more example? Let's say now that the first letter must be a vowel, A, E, I, O, or U. So that gives us 5 choices for the first vowel. And then when we go to get the next letter, we have 26 to choose from. Oh, wait, do we have 26? I didn't read this fully. Notice that repetition is not permitted. So it's not 26, but rather 25. Because I've used one letter. When I chose the vowel, I can't reuse that. And now when I go to get the next element, I've got 10 digits to choose from. But, oh, notice that the first one can't be a 0. So I don't actually have 10. There's only 9 to choose from. Notice when I go to get the second digit, regardless of what digit I used for this first digit, there's still 9 left. The 0 together with the 8 digits 1 through 9 that I didn't use, so there's 9 digits left, and then there's 8 left, and then there's 7. When you multiply this through, I believe that you'll find that there are 567,000 different options available. But try the multiplication yourself. 5 times 25 times 9 times 9 times 8 times 7. So this is how we'd use the fundamental counting principle. Notice this procedure one more time. I'm going to start by drawing in these lines for each choice that I'm going to make. And then I'm going to write what gets filled in with each of those lines, just like a description. And then on top of that line, above the line, I'm going to write the number of choices we have, the number of ways I can make a choice of a letter or of a digit, and so on. But I believe if you follow that process, those problems will go pretty smoothly. Let's move on now to a permutation. Now, what is a permutation? It's an ordered arrangement of a given set of numbers, or objects rather. So let's say that I have 3 balls. One ball has a 1 on it, one has a 2, one has a 3, and I want to put these in order. Do you see that I could put them 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. Or I could start with the third one and then go 1, 2, or 3, 2, 1. So I could actually list all the possibilities. And I see that there's a total of 6 permutations. There are 6 ways that I can arrange the numbers 1, 2, and 3. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. Sometimes when it's a small set, it's not too hard to list all the possibilities, such as this case where there's only 3 objects that we're arranging. But if we have a library of 75 books, and you want to see how many different ways can I arrange all 75 books, notice that it's not going to be quite as easy to do. Or what if I have 12 dinner guests, and these dinner guests are very picky about who they sit with or who they sit next to? How many different ways can those 12 guests be seated around your dinner table? Whether your dinner table is a square, a rectangle, a circle, an oval, the number of different arrangements is the same. The number of ways we could seat those 12 guests is going to be a permutation. We could also talk about 5 children lining up for the bus, or 25 children lining up to go to the cafeteria when they leave their classroom. And all of those are permutations or ordered arrangements. The key is that the order is going to matter. Now, if you're really interested in this and want to see some fun additional examples, you could look at the section on combinations. A combination is just how many different ways can we select things, but the order isn't going to matter. We're not going to look at this section as a required section. Section 11.8, combinations, but you may just find it interesting, so I want to recommend it to you. Let's look at how to calculate the permutations. Notice that a permutation is, if you're using every item available, the formula is just the n factorial. So when we said how many different ways could 5 children line up for the bus, well, if you think about it, we could say that we're going to seat all 5, 4, 5, and how many children can be first? Any of the 5. Once one of them's already first, how many can be second? There's 4 left. There's 3 left who can be third, 2 who can be fourth, and only 1 student could still be last. Notice that that's the same as 5 factorial. So how many different ways can you arrange 12 guests at the table? 12 times 11 times 10 times 9 times 8 times 7 and so on. And just to give you a reference for these, let me give you the numbers. 5 factorial is equivalent to 120. Can you believe that? There are 120 different ways for just 5 children to line up at the bus. For 12, how many different ways can you arrange those 12 dinner guests? Are you ready for this? These numbers just always astound me. 479,000,1600. 479,001,600 ways that we can arrange 12 people around a table. And that's how we calculate a permutation. Well, sometimes a permutation isn't going to use everyone. So here's an example of a permutation that's going to use this next formula. Let's say that instead of all the children in a class, let's say we have a class of 20 students, and we're going to do an experiment, and we're only going to use 5 of those. We would describe this as a permutation of 20 students chosen 5 at a time. Do you see how we'd calculate this with the fundamental counting principle? There's 20 students to choose from, so if there's 1, 2, 3, 4, 5 positions to fill, there's 20 ways to get the first one. There's 19 students left for the second choice, and then 18 for the third choice, 17 for the fourth choice, and 16 for the fifth choice. So if I multiply 20 times 19 times 18 times 17, I'd see how many different ways I can arrange 5 of the 20. So notice there's 20 students to choose from, but I'm only choosing 5 of them. This is another way to do this is this formula where I do 20 factorial, but notice what I've not used. Notice that I didn't use the 15, 14. If I did 20 factorial, it would have kept going from 15, and I didn't use those places. So I did the 20 minus 5. 20 minus 5 is what got divided out. That 15 times 14 and so on got divided out. So the formula would give us 20 factorial over 20 minus the number we're using, 5 factorial. So if we put this on our calculator, 20 times 19 times 18 times 17 times 16, you could calculate the result this way. You could also use your scientific calculator with that PRB button and find the permutation function there. Let's look at an example. A fishing club at Central New Mexico Community College has 9 members. And to determine the club officers, 9 slips of paper containing the names of the members are placed in a hat, and the advisor randomly selects a name from the hat to become president. The first person is the president, the second is the secretary, and the third is the treasurer. So do you see that we could think of this as arranging those members? We've got a permutation. There's 9 club members to choose from. We're only going to choose 3 of them. So we could read this, a permutation of 9 items chosen 3 at a time. A permutation of 9 items chosen 3 at a time, because we've got 1, 2, 3 names. So the first step to understanding this problem is being able to interpret it as being a permutation of 9 items chosen 3 at a time. When I write this out in the formula, I'd have 9 factorial over 9 minus 3 factorial. So that's 9 factorial over 6 factorial. I could simplify this by saying 9, 8, 7. Notice if I did 6, if I wrote the factorial all the way out, which I don't always want to do that. But if I write the factorial all the way out, and then I write the denominator, 6 times 5 times 4 times 3 times 2 times 1, all the way out, do you see that this 6, 5, 4, 3, 2, 1 reduces? So what I'm left with is 9 times 8 times 7. And if I put that on a calculator, I could get the final result. 9 times 8 times 7 is coming to 504. So there are 504 different permutations we can make. There is one more type of a permutation that you'll want to be familiar with, and that's a permutation where we have some repeats. But first, let's do one more example of this type of permutation. We've got a club with 10 different routes that members could choose from, and they only have 6 dates for their trip. So they're only going to choose 6 of those routes. So we want an arrangement of 10 items, 10 routes, chosen 6 at a time. So of those 10 routes, we're only going to use 6. You might be ahead of me already on this. If you wrote the formula out, 10 factorial over 10 minus 6 factorial. So that's 10 factorial over 4 factorial. So that's going to be 10 times 9 times 8 times 7 times 6 times 5. Because once I get to that 4, 3, 2, 1, it's just going to divide out by the denominator. So it's just 10 times 9 times 8 times 7 times 6 times 5. Go ahead and try that on your calculator. I think when you do that, the answer that you will get is 151,200. And that's how you could work this example. Let's do one last example, an example where you would have some repeats. So we've got some letters to choose from, and I'm going to put these in order so that I can see where we get repeat. C-I-N, C-I-N-N, A-T-I. So notice I have 2 C's, 3 I's, 3 N's, an A, and a T. This formula, permutation of duplicate items, is a formula we're going to use. A number of distinct permutations when we have some repeats would look like this. We're going to start with how many places we have. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters all together. So 10 times 9 times 8 times 7 times 6 times 5 and so on, down to 1. But then I'm going to divide out repeats. So divide out 2 factorial, 3 factorial, and 3 factorial. There's not a button on your calculator that'll do this one for you. So let me show you how we would do this. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we're going to divide by 2 times 1 times 3 times 2 times 1 times 3 times 2 times 1. Do you see what you could reduce out? Real easily we could reduce out the 3, 2, 1, but there's more we could reduce as well. Do you see the 6 here in the top? I could reduce the 6 by the 3 and the 2, and now I've got 10, 9, 8, 7, 5, 4. I could take the 2 and divide it into the 4. So what I'm left with is 10, 9, 8, 7, 5, 2. Go ahead and try calculating that on your calculator. Did you get 50,400? Let me show you a shortcut for that calculation. all you really needed was 9 times 8 times 7. And then we have times 10 is 1 0. Times 10 more is another 0. But that's it. Well, I hope that this helps you get started with the permutations. Please let me know if you have any questions about this concept. I'm available to help you however I can. And watch your course content box for more video examples walking you through some of the activities.